Hello again, physics friends. We are talking now about angular momentum, giving a definition for it and some motivation for why this quantity is useful. So when we think about angular motion, or maybe an object moving in a circle, we have the unfortunate reality, I guess, that the momentum vector is constantly changing as a function of where this particle is in its motion. So the p vector is constantly changing, even though there's something that's static about this system, right? The particle is just moving in a circle over and over and over forever. So it seems like there's got to be a better way to talk about this motion. That's one motivation. There's something constant about this system, even though it's not the momentum that's constant. The other thing to think about is you could have the same setup, circular motion, but maybe the particle is going in the other direction. So instead of moving in the counterclockwise direction, maybe it's moving clockwise. So these are different momenta vectors at different instants of time. And these two cases are different. The case on the left is counterclockwise rotation. The case on the right is clockwise rotation. They're both circular motion, perhaps at the same speed, perhaps in the same radius, but they're different. So not only do we want a quantity that can characterize this the constant nature of this circular motion, but we want it to be different or distinguishable. We want these two situations to be distinguishable in our notation. Okay, so the definition of this angular momentum of a particle is that we'll say the angular momentum of a particle, we'll call it lowercase l, is equal to the position vector of that particle crossed into its momentum. Okay, and if we look at the system, we see that the momentum vector is changing on a regular basis, and so is the position vector. It's moving. The direction of the position vector is changing. But it turns out that this quantity r cross p is not changing. So let's see why that is. So the magnitude of L vector is equal to the magnitude of r cross p. And as we've seen before, that's mag r, mag p, times the sine of the angle in between r and p. Okay, and r and p in particular are perpendicular for uniform circular motion. Okay, that's number one. So theta here is pi over 2, or 90 degrees. Also, the magnitude of r is just the magnitude of the circle. Let's say that circle has a radius equal to r, capital R. So our cross product has mag r mag p times the sine of pi over 2. Mag r is capital R. The magnitude of p is m times the speed, v. Okay, and the sine of pi over 2 is 1. So our angular momentum has a constant magnitude, right? Although the particle is moving around the circle, that circle has a constant radius, the mass of the particle is constant, and the speed is constant. So this product is constant. If we look at the r vector and the p vector at some instant of time, we'll have r in one way and we'll have p perpendicular to it. And r crossed into p, that's a counterclockwise motion, or if you use a right-hand rule, you do r cross p, your thumb points out of the page. Okay, so in this problem right here, the angular momentum points out of the page. Okay, the direction is never changing, r cross p at all points along the circle point out of the page, and the magnitude of L is unchanging, and so indeed we found a quantity for this system which is constant, both in magnitude and direction. Constant magnitude, r and v, constant direction, out of the page. So this seems like it's doing the thing we're hoping for, a single quantity that doesn't change even though the linear momentum of the system changes. Can it also distinguish counterclockwise motion from clockwise motion? Well, let's take a look about that. Well, we still have R and P perpendicular. This time, however, R cross P, that's a clockwise rotation. So we have the angular momentum, will be into the page. So L is into page. So it's the opposite direction from the first case. How about the magnitude of L? Well, it's still mag R, mag P, sine of 90 degrees, which is still big R times M times V. So it's the same as before. So what we learned is if we have uniform circular motion, we have a constant angular momentum, and if we flip the direction of that circular motion, we have the same magnitude for that quantity L, but we've just flipped the direction from out of the page to into the page. So we do have a quantity now, this angular momentum quantity, that can distinguish counterclockwise from clockwise rotation, and it's a constant of a motion like this. So next I want to make a comparison or analogy between linear momentum and angular momentum to motivate the rotational analog of linear momentum, and then we'll see, once we've defined this angular momentum, we'll try to understand how you change the angular momentum of a system or a particle, and we're going to learn that there's something called torque. In order to change the angular momentum, you must apply a torque. So we'll get to that next. Okay, so we'll start by motivating angular momentum first by reminding ourselves a little bit about linear momentum. And we'll use as a framework we'll ask our question of how can you measure the linear momentum of a speeding bullet? So for example, we have this bullet, it has some initial velocity and it has some mass. Before the era of high-speed video, how would we be able to measure the momentum of this bullet, okay? Well, one way that people came up with is to shoot it and embed it in a block such that after the bullet is embedded in the block, that system of bullet plus block will move horizontally to the right. And because there's no external force on the system, we know there's no net external force in the x direction on the system, and by system I mean bullet plus block. We therefore know that px, the x momentum, is constant. So that px initial equals px final, and the x initial, the initial momentum is little m moving at velocity vi with the big M at rest. And at the end of the day, you have all of the mass, little plus big M, moving at some final velocity. So in that case, rather, you could find the final velocity as the ratio of these masses times the initial velocity. And that's related to the bullet's momentum divided by the sum of the masses. Okay, so once you've determined the velocity of the bullet, you can weigh the bullet and determine the momentum of the bullet coming out of the gun. So in this case, the final speed of the system after a collision is a measure of the initial momentum of the bullet. So let's think about a rotational analog of this. Okay. In particular, we want a situation where we have a collision, or we collide, and then we stick together. So a completely inelastic collision, if you like. And one scenario that I have in mind is a kid running and jumping onto a merry-go-round. Okay, so kid jumps onto a merry-go-round. Okay, and the situation might look something like this. This would be a top view, meaning we're up above looking down. We have a merry-go-round that's pivoted, and that merry-go-round can spin, but it cannot translate. And then we have this kid over here that's running with some initial momentum. We'll call it P kid. And the kid's going to run towards the merry-go-round, jump onto it, and land. Okay. And we're asking the question, what is the angular speed of the merry-go-round after the collision? Kind of an analogy to what is the linear speed of the bullet and block after the collision. So in fact, I'm going to draw a second diagram here, which is the after. So if we compare the linear and the angular cases, in other words, the linear case with the bullet and the block, we have a bullet and we have a block. And the analogy here is instead of a bullet, we have the kid. Instead of the block, we have the merry-go-round. The bullet carries in some linear momentum, which we could call P bullet, and the kid is bringing to the system or contributes to the system some angular momentum. After the collision, the block and the bullet move with some final velocity, and after the collision of the kid jumping and sticking onto the merry-go-round, we'll have a final angular velocity, omega sub f. So if we think about what matters in this problem in terms of affecting this angular velocity, omega f, where the kid lands is going to matter, right? If the kid runs and jumps and lands on a line through the origin, that's not going to create a rotation. If the kid lands up here somewhere in the top half of the merry-go-round will rotate clockwise. If the kid lands down here in the bottom half of the merry-go-round will rotate counterclockwise. What else? If the kid lands near the rim, that might create a different amount of rotation, different magnitude of omega f, versus if the kid lands closer to the pivot. And also, if the kid is running faster, in other words, if the kid has a larger linear momentum, that could also create a larger angular velocity after the kid lands. So things that can affect the angular momentum include how far from the pivot the kid lands, so the magnitude of r. So the angular momentum can depend on the magnitude of that r vector, can depend on the magnitude of the kid's momentum, that vector, and also the relative angle between momentum of the kid and where the kid lands. Okay. In particular, as theta goes to 0, we get no rotation. As theta goes to 90 degrees, we get maximum rotation. Okay. And just as in the linear bullet case, the momentum of the final system came about because of the momentum of the bullet. Here, the rotation of the final system came about because of the angular momentum of this kid. So the angular momentum of the kid must depend on things like magnitude of r, magnitude of the kid's momentum, and also the angle between, where when the angle is 90 degrees, we get maximum angular momentum. When the angle is 0, we get none. So we might expect that there's a proportionality not to theta, but to sine of theta. Okay, well, this is exactly, if we just assume everything is proportional to these terms to the first power, that just motivates all of these terms being multiplied together, and we get that expression that we've seen before, that the angular momentum depends on magnitude r, magnitude p, and the sign of the angle between it. So L equals r cross p is consistent with that, but how can we distinguish that from L equals p cross r? Both of those will have the same magnitude, mag r, mag p times the sine of theta. So we need to talk a little bit about the direction of spin. Well, that's pretty straightforward. We can get the direction of the spin based on whether the kid lands down here or up here. So if the kid lands down here, then we have a counterclockwise rotation, and we want r cross p to point out of the board, because a counterclockwise rotation is a rotation out of the board. That is consistent with r cross p. So thinking about the direction of the rotation after the collision helps us select r cross p and reject p cross r. Okay, so this angular momentum equals r cross p, that is a fundamental definition of the angular momentum of a point particle. And if we talk about the angular momentum of a system consisting of many point particles, or a rigid object made up of lots of atoms of point particles, then we can build up the angular momentum expression by using this expression for each of the objects in the system. Okay, well, now that we have a definition of an angular momentum, we might wonder, is there an analogous Newton's second law for rotations, right? So we know that there's momentum and Newton's second law, linear momentum, and Newton's second law tells us how to change the linear momentum. Now we know about angular momentum, right? We know L equals r cross p. How do you change L? What does it take to change L? Is there a Newton's second law for rotations? Okay. So we're going to start, in fact, with Newton's second law for linear motion. And from there, we're going to derive the fact that a torque is required to change the angular momentum, where this torque is defined, as we'll see in a minute, to be r cross F. So we need a force acting at a specific location in a specific way in order to bring about a change in angular momentum. So let's see how this all comes to be. Okay. So we'll start with Newton's second law, and we'll start with we need a force to bring about a rate of change of momentum. And if we take the cross product of that whole equation with r, then on the left-hand side, we have r cross F, and on the right-hand side, we have r cross dp dt. Okay. Now, for a minute, consider the quantity as a mathematical aside. Consider the time derivative of r cross p as a quantity. Well, we're going to get, just as we did with the dot product, we're going to get a product rule, dr dt cross p plus r crossed into dp dt. Okay. Well, dr dt is simply the velocity. So I can rephrase the first term in that way. What do we know about the velocity and the momentum? You know, if we have a velocity pointing to the right, what direction does the momentum point? Well, it's got to also point to the right because p is equal to mv. So whatever direction v points, that's the direction that p points. What do you get when you cross, we take the cross product of two vectors that are parallel? Well, you get 0. So this first term is gone. And so we're left with r cross dp dt. But notice that's exactly what we had on the right-hand side of our Newton's second law that got modified. So these two quantities are equivalent. We can reframe the right-hand side as the time derivative of r cross p. But that's cool because we know that r cross p is exactly our angular momentum. Oops. And so we find this expression, that in order to change the angular momentum, we not only need a force, but we need a force acting at a location such that the cross product of the position vector of the force and the force itself is non-zero. We need a torque. So this quantity, we give just a name. We call this the torque. And we give it in this class the symbol capital Greek letter gamma. So we end up with a Newton's second law for rotations. And that will be torque is equal to the rate of change of the angular momentum. As a very straightforward example, let's come back to uniform circular motion. We showed already that the angular momentum was constant, even though the linear momentum changed. So if we come back to that same diagram that we started with, we have circular motion, we have a linear momentum vector, we have a position vector, and we have angular momentum, which is r cross p, is a constant. The magnitude of that angular momentum is rmv, where capital R is the circle's radius, and the direction, which you might call L hat, in this case, is out of the page. Okay. If L is constant, it must be the case that the torque is zero. So let's verify that the torque is zero. Recall the torque is defined to be r cross f. Okay, we already know r, that's the position vector to the particle. What direction must the force point for uniform circular motion? Well, we know that for uniform circular motion, the net force is radially inward. So let's imagine that there's a force exerted on this point particle pointing toward the center. So we have two vectors. We have r and we have f. And those two vectors have an angle between them of 180 degrees. So r cross f is going to be 0 because the sine of that 180 degrees is 0, and mag r mag f times the sine of theta is the magnitude of r cross f. So indeed, there is no torque in this example, and there is no torque not because there's no force, but rather because the force and the position vector to the force are anti-parallel, and therefore there's no torque that results from that force. Okay, so we've introduced angular momentum, we've introduced Newton's second law for rotations. In other words, to bring about a change in angular momentum, you must apply a torque. And we've shown a very simple example of a situation where angular momentum is constant and torque is 0. Those are two equivalent statements. We're going to have a lot more to say about angular momentum, but that will come in a future video. So for now, take care and be well, and we'll see you next time.